You know the method, derivative method, hypergeometric function.
I'm not so sure.
So go to the last page and look for the keyword, and it'll give you the page number. But it is, I can give you, I mean, that's what, because somebody else also asked. But I'm just saying you can check. That's the easiest way to check, okay? Because you know the method, you just look at the constraint hypergeometry and it'll give you, okay? But the derivative method is in this chapter. Okay? The other things, constraint hypergeometric and hypergeometric are these two sections, okay? Maybe now. So, but because we are doing, everything is between chapter 16 and 18, whatever we are doing, okay? I mean, but we are doing different parts of it, right? I mean, methods and some then the special function required. Otherwise, you just keep on doing methods, then we'll get bored. I mean, you have to see, examples of why we are doing what we are doing. So, but everything that we do is in the book. So you have to know the method that I'm doing, whatever it is, and look at the last pages. The not what is it called? Not bibliography. I mean, I'm just kidding there. Not table of contents. Table of contents is always from
Index.
Index, yeah, index. I'm just saying it's completely blanked out. Yeah. So look at that, and then you'll know where it is, because it gives you the page number. Okay, so you go to the exact page number. So that's how you check.
Thank you.
But everything is between 16 and 18. We'll keep on going back and forth between even the inhomogeneous differential equation, right? Because we are developing in a certain way. What we want to get started today is inhomogeneous differential equations. So far we've been doing only homogeneous differential equation, right? I'll teach two methods for teaching this inhomogeneous differential equation. Both are based on the Green's function method, but how you calculate the Green's function is different. Okay, so that's what we are going to be doing. And I think I said a long time ago, like, if you did not know anything, you can solve the homogeneous differential equation, and brute force method would be something that satisfies. This is an nth order differential equation. So this is nth order differential equation, so it will have n solutions, right? I mean, so far we're doing second order, it has only two solutions, y1 and y2. Nth order will have n solutions. So what we have to do is, supposing we did not know any method, like the Green's function method, you would solve the corresponding homogeneous differential equation, right? And get that solution through the methods that you know. So if it's a second order differential equation, you have two solutions, y1x and y2x. So the general solution was, linear combination of y1 and y2. But this is nth order differential equation. So if it is like this, it will be linear combination of some n solutions. So whatever you get by solving the homogeneous differential equation is called complementary function. Okay. And if you want to solve the inhomogeneous differential equation, the brute force method would be just guess something. It's an operator operating on this y, right? So can I add to this something such that the right hand side is not equal to 0? this Yx is just, this is the complementary, the linear combination of all the solution plus a particular solution which satisfies the differential equation. So that would be just, that cannot be done in general, right? I mean, it can be done maybe in a second order differential equation or maybe first order inhomogeneous first order differential equation, you can guess. But that's, just a very general philosophy. But you can see in principle is not going to be practical at all, so that's why we need to have new methods, okay? So that's what I'm going to do, but this is just to tell you what, if you did not know, this is maybe you'll be just guessing what is it I have to add to the solution that you get from solving homogeneous differential equation that will satisfy. I'm going to write it now in a compact notation, okay, where L is your differential operator, L, right? Because I'm going to get into that notation too. I mean, L is a linear operator, which is nothing but all these things. Okay, this is just an overview of what inhomogeneous differential equation is all about. Let's get started on what I want to do today. This is so we're trying to solve something of this nature, where L is your differential operator, second order, if it's second order, or whatever it is. It's a differential operator, right? So, so the principle in which method that we are going to be using is called as eigenfunction method, and I'll tell you what it exploits, many things. So the method that I'm going to use is an eigenfunction method where it exploits the linearity of this operator, okay? And this we are trying to also solve in certain domain, okay? And we are going to solve this inhomogeneous differential equation subject to some boundary conditions, okay? You will know what this is given, okay? These are given. Boundary conditions are given. So this operator L, which is a linear operator, which we know, becomes Hermitian operator. This is what we are going. This is why the eigenfunction method comes. Becomes a Hermitian operator if it satisfies certain condition. Okay. So L is your differential operator, okay, like this. I mean, if it's second order differential equation, it is of this form, right? I mean, there may be some coefficients here, right? I mean, a to x, or px, qx, whatever you want to call it, a1x, all right? Plus whatever it is, okay? It's some operator, okay? We'll talk with respect to a problem later on, but it's a linear operator or something like this. Or maybe there's something else, also plus qx or whatever it is. There may be a constant too, right? There may be another term too. Without y, right? Y is it's operating on that. So part of the differential equation is just a differential operator and it's a linear operator. But that linear operator, it becomes Hermitian operator. Supposing it becomes Hermitian operator, then what we are going to do is the following. If L, this operator, is Hermitian, okay, I'll give you some condition. I will prove all that also later on. That is, L dagger has to be equal to L and stuff like that you know from quantum mechanics. Okay. If L becomes Hermitian, what we are going to, we know, I will also write down something. We are trying to seek the solution Yx, okay? That's what we are trying to seek, okay? eigenfunction can be written as the superposition of in a complete basis, right? I mean, you know that. So the basis that I'm going to use, if L is an operator, a linear operator which is Hermitian, is the eigenfunction of that linear operator. So the solution that I'm going to seek, I can always write it as linear combination of some complete basis set, which is nothing but the eigenfunction of the Hermitian operator. For this operator, for any differential equation to be Hermitian, there are certain conditions it has to satisfy. This is where I always kept on saying that if you remember when we were doing the Legendre differential equation, this, let me call it like this, Px d square y dx square. If I wrote it like this, so maybe I'm just going to use a slightly different notation, doesn't matter. Supposing I had a differential equation like this, and I had always emphasized this point, if the coefficient Rx is equal to P prime x, then that corresponding operator, linear operator, becomes automatically Hermitian. So in such cases, L will become Hermitian. And in such cases, I can write my solution as linear combination of superposition of eigenfunctions, where Yn actually satisfies, is an eigenfunction of the operator L. Okay. So for such differential equations, which are called Sturm-Liouville equations, I'll first generally talk about the concept so that you understand. The Legendre differential equation was a Sturm-Liouville equation, right? I mean, we could write it like this: 1 minus x squared y double prime minus 2x then the L operator in this case, of course, is negative of that, because I want to also write it in this form Ly equal to lambda y. L operator here is nothing but, in this case, negative 1 minus x squared d squared over dx squared minus 2x, or plus 2x, because I have to put it on the other side. The L operator for the Legendre differential equation will be this. So we can write Ly in this case as L times L plus 1 times 1. Right? This looks like an eigenvalue equation, right? I mean, where the eigenvalues are nothing but your Legendre polynomials order. So it has been proved, which I will prove maybe next class, that if I have a differential equation of this form with the coefficient of the first derivative to be exactly equal to the derivative of the first term, that operator, that's corresponding differential operator from that particular differential equation becomes Hermitian. Okay, for such differential equations, I can use this method. That's the important. I cannot blindly use this eigenfunction method. I can use the eigenfunction method if L is Hermitian. So not all differential equations fall into this category either, but there's also a way to do that. Any differential equation which is not even, doesn't automatically satisfies Hermitian, doesn't fall into Sturm-Liouville, I can multiply by certain factor, it's called integrating factor, and you can force it to be, Sturm-Liouville also. So there are lots of tricks also. Okay. But we will be right now considering operator which is Hermitian, some differential equation where it is already Hermitian, and not only it has to be in this form, it also has to satisfy the eigenfunctions. They have to satisfy certain boundary conditions. So the method that I'm going to give you is valid if, let's say y could be solution of the homogeneous differential equation, x, p of x, p of x is the, not p of x that we normally have been calling, is a coefficient of the second derivative. P of x for us in the Frobenius series was, we had to divide it through, okay. Is the coefficient of the second derivative term, yjx, evaluated between a and b. This, it has to satisfy this condition for the operator L to be Hermitian. Okay, so these things I'm going to prove in the next class, but for now, what we're trying to do is solve an inhomogeneous differential equation in a certain domain, okay? And in that domain, the L operator will be Hermitian if the solution of that operator satisfies this boundary condition, which means the following. This can be satisfied in a number of ways. This is what I mean by this is subject to some boundary condition we are solving. So you have to watch for the boundary condition. What is it given? Does it satisfy? Okay. This is one of them is derivative. Okay. So either the solution, this can be satisfied in a number of ways. The solution is 0 at A, at the boundaries. So that term will be 0, okay? The other way to satisfy, of course, is P of A or P of B equal to 0, okay? That can also be, that's a way to satisfy. Or you could have a combination of things, but it could be also the derivative can be 0, okay? So what you have to see is what is the boundary condition you are asked, given in a given problem, to make sure whether this method can be applied. So there are several things you have to check before you use this method or whatever I'm going to develop next time. Okay. So right now, so let us say if it was like this, I know it will satisfy this condition. So watch for what is given here. If ya equal to pi or something, maybe you cannot do it. You understand? So that's what you need to. So the boundary condition is important, the important factor here. So you're solving an inhomogeneous differential equation subject to certain boundary condition. Yeah.
So it's yi star and then yj prime.
Right. That's a derivative. Yeah.
Okay. I just make sure. I didn't see the j's on the other side or anything like that.
Yeah, it doesn't matter. It is even one of the terms is 0.
Mm-hmm.
Okay. It is just eigenfunction. Okay. You can it's just different eigenfunction, different states you can think of. Okay. Now, what I'm trying to say is this can be satisfied because these are all solutions of this differential equation. Either the solution itself at A and B are 0, or the derivative of the solution at A and B have to be 0. So this may it will become clearer only if I prove this. I mean, right now it is just a different, because this is a different solution, right? Depending on L. If it is a second order differential equation, it has two solutions, y1 and y2. So basically, what I mean is one of them is y1 at A is 0. y2 prime at b is 0. That's all it means. So I and j and all that, that's all it means. Okay, so it is here j. So it doesn't matter. Okay, I mean, so you can, right now it doesn't mean anything. What I want you to know is the solution, this condition, there are various ways to satisfy. Either the solution at the boundary is 0 or solution and its derivative, one of the derivatives 0. Because what it means is the following, right? Y star x, x equal to A, E A, y j prime, okay, minus y prime. They also have to be same. They have to be same and equal to 0. So the way to, if one of them is 0, of course, let us say, if this is 0, this term will drop out, right? And if yb is 0, that term will be dropping out, right? So, so we can have the second or one other solution at A can be 0. The derivative of second solution at A could be 0. Derivative of the second solution at B has to be 0. So there are various ways.
So, but they have to appear in sets. You have to have.
Yeah, I think so. Yeah.
So you can't have y star A be 0, y star B not be 0, but
It
derivative.
has to be like this. Yeah, you're right. Ya equal to yb equal to 0. Because both terms have to, or I could have this. I can have in one term, this is 0, let us say. The boundary condition you may be given in a given problem is, that rarely happens, but it could be, right? Yj prime at b equal to 0. Then
Okay, so
also the second term, that can
So you
come.
can miss.
Yeah, so that can have, you can have a, solution or solution and its derivative can be given, okay? So most of the time it will be like this, but there are problems where you may have, y prime of the solution has to go to 0 also. The second solution has to become 0 or something like that. So that's all you have to watch out for. But most of the time you'll be given, homogeneous boundary condition. The solution at A and B is 0. Okay, so that's all it is. But these conditions come from. You need to a little bit know about Hermitian operator theory. That's why I don't want to mix it up today, but I'll develop that separately. Okay. So for this method, what we're doing is eigenfunction method. So L has to be Hermitian, and L can be Hermitian if you have appropriate boundary condition on the solution or its derivatives. Okay, most of the time you have the solution, whatever solution is seeking at the boundaries are exactly equal to 0. Okay? If that's the case, you can happily apply the eigenfunction method because it will satisfy the general condition that I gave you for the Hermitian operator, and that I'll prove next time. Okay, so so right now for the moment, you can all you have to know is there's some boundary condition, and your operator is Hermitian. All right. We also know any function. I gave a problem yesterday, homework problem, expanding Dirac delta function in terms of Legendre problem. Why did I give that? Because I want you to understand. Listen, any function, if you have an infinite series, you can expand that into, and it is, Legendre polynomials could be used as a basis, basically. That's all. That was the reason for giving that problem in a very simple way. That's what was happening. There you are, some function, which is in that case Dirac delta function, was being expanded in terms of Legendre polynomial. Now I'm just saying, okay, I don't know what the solution is, but if I have a linear operator and satisfy an eigenvalue equation, it's an infinite set. So then I can write any function in terms of the eigenfunction. So that is the. So our starting point is that. Okay, it is also, we don't know anything, but I'm trying to say, okay, I can write Yx in terms of that because L is a Hermitian operator. It's a Hermitian operator. Maybe I can write an eigenvalue equation corresponding to that, right? I can write it for the same operator L. Maybe I can. I have to solve, I mean, this is an homogeneous equation, but corresponding to, this operator L, maybe there's an eigenvalue equation. And what is that? All that we have to solve. All right, so Lipid abstract, Lipid quantum mechanics is there. In this method. So let's, now what we're trying to do is this, right? L operating on Yx. I have to find this. I can pull the L inside, go to Fx. I can write this, right? All I've done is for Y, I substitute that, and then I pull the L inside. Is this clear? Okay. What else can we do? L operating on Yn. Yn is eigenfunction. Okay, this is a solution of, this is eigenfunction. When I put a substitute, it's an eigenfunction of the linear operator. Good. All right. What can I write for L operating on Y and X? That's eigenvalue equation, okay? So I'm going to make this also a little bit more complicated. This is general eigenvalue equation, normal eigenvalue equation. The generalized eigenvalue equation is normally given as lambda n, some weight factor, y n x. Okay. So that is called as generalized eigenvalue equation. This is normal eigenvalue equation that you normally encounter. All right. If L is Hermitian, so the important thing is this is Hermitian, right? What do you know about eigenvalue and eigenvectors for a Hermitian operator?
Eigenvalues are real.
Eigenvalues are real. What about the eigenfunction? What is the property that we know?
Either all real or all
Eigenfunction. Okay, and eigenvalues are real. That's one of the properties. Okay. What do we know about the eigenfunction? That's the main property of Hermitian, operator, Hermitian matrix, which you come across. I mean, if you cannot think of an operator, think of a Hermitian matrix. What are the properties of eigenvalues and eigenvectors for a Hermitian matrix? You can think about. They are orthogonal. So that's what we are going to exploit here. So we know that in this interval, y star nx, ymx has to be like this, right? I mean, if n is not equal to m, this is 0, n equal to m, it is 1. Okay, so we know they are orthogonal. The only difference when you have a generalized eigenvalue equation is you have a weight factor. The orthogonal property will be slightly different. Okay, you will write y star nx, whatever this weight factor is. Okay, y sub mx dx. Put it as 0 for n not equal to m. It's easier for you to understand that way. Okay, let me just put it up. Okay. For n equal to m, it will be 1. Okay, so that's what it is. Okay. All right. So let's just start. I'm going to write it generally at this point. So L operating on Yx is nothing but summation n going from 0 to infinity, C sub n, and this is nothing but lambda n rho of x y sub nx equal to f of x. All I've done is use the eigenvalue equation, right? Written it generally, it should be lambda n y and x. Instead I have put a rho x also. Okay, I'm just going to multiply by y star mx and see what happens to this. Okay. So what I have is multiply by c star mx, and then let us try to, and I can sort of employ the orthogonal property, because I want to get this coefficient Cn, because I'm saying my solution can be written like this. I want to write my yx in terms, the only thing I don't know what is here is Cn. I know yn is solution of the Hermite eigenvalue equation, right? So I'm trying to somehow extract out Cn from this, okay? So to do that, so first step is I've done this, multiply c star mx and then integrate between a with respect to x or z, whatever, we'll see whatever, x integrate between a and b. We'll check the variable in a minute. So I have a to b c star mx fx dx sorry, ymx, my sister. I want to apply that one on the eigenfunction, right? Fx dx is equal to, let's write it, let's see how to write it. I want to write nicely so that, okay. Right, okay, I've got n going from 0 to infinity, c sub n. The integration is over, I need to apply that orthogonal relationship. Okay, yeah, I can a to b, we can rearrange it a little later. C sub n going from 0 to infinity of lambda n is there, rho of x, y star mx, y and x dx. This is what I have, but the integration is over the variable x. So all that, we can just pull this integration in, right? So what do we get? Because I want to apply this theorem, right? What we have is this 0, a to b, y star mx, y and x, rho of x dx is what I want to get, right? I mean, that is delta n, direct delta function n, comma n. So the right-hand side will become what? If I pull this integration now inside, what is that? So what is this term? So what is happening to the right hand side? What happens to summation? It contributes only when n equal to m, right? So what do we have? Cn lambda m. Okay, so my right hand side is now simplified to the following. This is nothing but Cn lambda n, a to b, y star mx, f of x, dx. So I have an expression for Cn, which is a coefficient factor. The coefficient in the superposition of solution in terms of eigenfunction is nothing but 1 over lambda m integral between a to b of y star mx f of x dx. Okay, that's what I get. And we started out with this, right? Any function, which is a solution, let's say, of this differential equation can be written as this, as a superposition of eigenfunctions in this case. Complete basis set, in this case, the complete basis set is your eigenfunction. Now, I have now an expression for Cn, right? So let's write now the solution as follows. So I can see Cn, I'm going to write like Cn so that I don't mix up some indices. I can write it like this. M is equal to n. Nothing, I'm just changing the label so that I can have it correctly. So my solution is nothing but n going from 0 to infinity of the following stuff. Okay, we got summation integration. Let's Cn and y and x. Okay, let's put x also here. And my Cn is that. So basically, what I have is the following. I need to do one more so that we don't mix up, okay? This is x, right? Here, this is a dummy variable, right? I mean, this x is a dummy variable, so I don't want to keep that. So we have to write it so I get the correct expression. I can write it like this. This, why am I doing it? Actually, this is what is going to give me the Green's function eventually. Okay, so substitute for Cn now. So I get y of x is equal to the following: a to b. Summation n going from 0 to infinity. Okay, I have y and x, y star and z, and I have lambda n. Okay, and then I have f of c dz. All right. So the solution of this in homogeneous differential equation, if L is Hermitian operator, is nothing but the following. That's all you have to know. Is integral between a and b, and this quantity within the summation is what we call as Green's function. I'll just call it function of two variables, x and z, f of z, d of z. Where f is your inhomogeneity in your differential equation. That is. So what this method says is the following. If you can calculate the Green's function, because this is known, right? I mean, this is part of the differential equation, you know that. If you're able to calculate this quantity, you can get the solution of the differential equation. Okay, so as simple as that is you have an integral to solve. And what is this Green's function? This Green's function is nothing but the following quantity. It's a function of two variables. What are these quantities? Eigenfunctions and eigenvalues, right? So, and where do they come from? They come from solving this particular equation, okay, lambda n yn, or lambda n, if you would generally lambda n rho x y n. So, given an inhomogeneous differential equation, if L is Hermitian, that is, it has to satisfy a certain boundary condition, then you can, for that same operator, you can write an eigenvalue equation, okay? And if you can solve that eigenvalue equation and get eigenvalues and eigenvectors, you can construct the Green's function. And once you have the Green's function, you can calculate the solution. Okay, so that is the method. Okay, so I'll just summarize it so that you understand. We have to do it because there's some abstract concepts are involved, and quantum mechanics also involved a little bit. So all we started was, okay, we have to solve this, but any function, I can write it as being if you have a complete basis set, you can write it as superposition of those complete basis sets. And what are those basis sets? If L is an operator, if L is a Hermitian operator, they are nothing but your eigenfunction of the linear operator. Okay, so that's what we did, and the rest was so basically these are the important steps here that we went through. The rest is detailed, but this is what. So this is our goal, and what we said was, if L is Hermitian, then I can write, maybe there's an eigenvalue equation, right, corresponding to that, I can write. And we also know this is not that trivial, it has to satisfy some, the solution has to satisfy some boundary conditions. That has to be checked for each problem that you're doing using this method. Okay. Which is really this, which I have not proved, but I'll prove it next time. Y px, yj, between A and B is 0. If this is the case, then I can write the solution as linear combination superposition of an infinite basis set. That basis set is nothing but eigenfunction of this linear operator. Okay. And if these things are all satisfied, then I can write this solution. We just evaluate what this coefficient should be, and then based on that, the solution is nothing but the integral of the Green's function, which is a function of two variables, f of z dz, okay, where g of xz is nothing but y and x, y star n in Z is divided by lambda n, which is eigenvalue. So these are eigen functions corresponding to the Hermitian operator. And this is your eigenvalue. Okay. So the Green's function, this is the method we are using today. Next time we are going to use a property of the Green's function that is basically the boundary condition of the Green's function will apply, and then we solve the problem. So for that, the starting point is something else. So I just want you to understand what that is. If I operate L on Yx, what do I get? This is my y. Okay, this is a solution. But that's also that, right? So if I operate L on this, what do you have? A to B, L operating on G of xz, f of z, dz. That's what we have, right? And what is this? L operating y is also what? That is my homogeneous I'm trying to solve, right? So this also equal to f of x. So what can I say about g of x? What can I say about L of g operate x of z? So what I have is the following: A to B, L operating on So what can I say about L operating on G? How can I satisfy this relationship?
It's a transformation. You're going from f of x to f of z.
No, I just want you to think about as an integration, so that I can have this quantity on the right hand side. Dirac delta function, okay? So it is L operating on G of xz should be nothing but delta of x minus z, okay? Because if I did that, the only time in this integration is going to survive, because of the property of Dirac delta function, this integral will survive only when x equal to z, right? So we right hand side equal to left hand side. Is this clear? So this is an important property. It's almost like, you know, the Green's function is almost like solution of the homogeneous differential equation. It's not x equal to 0, x is not equal to z, it's 0, right? So you can see something about the property of the Green's function, okay? I mean, it survives only at x equal to z, at everywhere else it is 0. So you can exploit that property to construct the Green's function. That's what we'll do next time, okay? This time, what we'll do is, we'll evaluate this Green's function using its definition, which is based on the eigenfunction. This method is clear, at least, I mean, the details may be getting lost because we have several concepts coming. I mean, some quantum mechanics concepts coming, linear algebra concepts coming. All we have is, we're trying to solve this. In order to solve that, you need to erase that equation, okay. We need to construct the Green's function. Okay. So this is very general, whether you use, this solution is very general, right? Whether you use the eigenfunction method or another method, you somehow have to calculate this quantity. Okay, that's all you have to know for the moment, but there are other details, and we are going to today use this method, okay, to solve it. So if you have a, for instance, this is why I keep on going to a Legendre polynomial. We know the solution. We know Yn is PLX. We also know for that differential equation, what is lambda? Lambda is L times L plus 1. You can rewrite that. So in such cases, you can, in that differential equation, you already know how to construct, because you already know the solution. You have done Legendre polynomial, right? A differential equation, the solution of PLX, Pn, and you know this eigenvalue, which is L times L plus 1. So there are certain equations where you can construct the Green's function very quickly through this method. All right. Let's just summarize that so that before solve the incident domain, the Green's function, f of z, dz. Two variables. These are the only important things that you have to know. Okay? Those probably we have some boundary conditions here. Here's the problem. There's one other place, right? We can, that L is Hermitian. For L to be Hermitian, we have to check that. If you have a boundary condition like that, L is automatically Hermitian. And if it's like the coefficient of first derivative is differential of the second derivative, that's also Hermitian. Okay, so that's okay in Legendre, but not in Hermite or what is it called, Laguerre. Okay, those are not automatically. Okay, so we have to do some tricks there. All right, one more part. I'm not proving it, but you can check. But I don't think we directly need it for our method. These are some properties of the Green's function. This is a very important property of the Green's function. It's almost like the Green's function is satisfying the homogeneous differential equation. Okay, so if you have unit force, it has a solution at x equal, otherwise it's 0. Okay, so it's easy to remember that property. So, okay, so that's the important thing. Let me just do an example so that's not so abstract. Okay, so that's a homogeneous differential equation we are trying to solve. So is the first derivative, in this case, you can first check. I mean, the coefficient is 1, right, of the second derivative. There's no first derivative, so it is 0. So it's fine. It's already in Sturm-Liouville form. So it is automatically this operator L, in this case, is Hermitian. Okay, so you have a differential equation, right? So here the first term is 1, right? You don't have the first derivative. So derivative 1 is 0, right? So it satisfies the condition that P of x. Supposing we had it like this, right? I mean, x. This had to be derivative of that. If that condition is satisfied, the corresponding L operator is Hermitian. So it is Hermitian in this case. And also we are solving this subject to this boundary condition. So all inhomogeneous differential equations are solved subject to some boundary conditions. We're using this method or other method. so it also satisfies that kind of a boundary condition. Okay, so you know this is a good case for applying eigenfunction method. So I can apply the eigenfunction. So first you have to, given a different inhomogeneous differential equation, you need to check which method I have to apply. And if L is Hermitian, yes. So your L operator in this case is what? And I want you to again and again, what I mean by L here. What is the L operator here? Plus 1/4, right? Okay. So L is operating on that. That's f of x is sine 2x, right? So those things are clear. All right. So L is Hermitian. So what can I? So what is the next one? If L is Hermitian, I can write L y n x equal to lambda n y n x. I can do that, right? So this is my differential. So the next step is, can I construct this, right, for this differential equation? An eigenvalue equation can I construct? So if I wrote that, what is it? The next step would be what? I have to write d square y n x squared. I can write this, right? This is my L operator plus 1/4 of yn. I'm not putting y, you can see it. This eigenfunction, subscript is eigenfunction, right? Yn x is equal to, what should I write on the right hand side? So L is Hermitian, so I can construct an eigenvalue equation like this. Okay, and I'm going to write my solution in terms of this. What is the solution of the eigenvalue equation? So this is an eigenvalue equation. It's not your original inhomogeneous equation. What is my right hand side? Because this is your L operator, right? L operator operating on the eigenfunction corresponding to that linear operator. Then what's the right hand side?
Y or lambda n y.
Lambda n y n. So I'm right. So I have to solve this differential equation to evaluate what is yn and what is lambda n. Okay. So if I did that, then I can construct my Green's function. Okay. So this is a very simple differential equation. We can calculate. We can solve it. Okay. So we have to solve for. We did that. Solve for yn and lambda n. That's what we have to do. How can I solve this? We've done several differential equations, right? Can I write it like this? All I've done is just moved it to the other side. If I write it like this, are you able to guess your solution? What does it remind you of this differential equation?
Harmonic oscillator.
Harmonic oscillator, yeah. D square y or dx squared is minus omega square y or something like that. It's harmonic. So it's a combination of sine and cosine. So that you have to recognize that quantity within parentheses as omega square, not omega, right? Because that's what in harmonic oscillator you have. And so if you have like this, then the solution is y of nx is then what? A n sine of something is b cosine of something. And what is that something?
Square root of.
square root of that, right? But this omega, you have to think of this as omega squared, right? So this is now square root of 1/4 minus lambda n, right? Square root of 1/4 minus lambda n, okay? So if you've forgotten, d square y over dx squared is negative omega squared y. This is a harmonic oscillator solution. Then y of x is nothing but a sine omega x plus b cosine omega x. This is what we started. This is our first differential equation we started with in this course. Okay. All right. Now what? We start applying the boundary condition. So we can solve this, right? Yn and x equal to 0 is 0. All right. So what does that mean? Implies the coefficient Bn is 0. Right. Then we have the other boundary condition, Yn at x equal to pi is 0. Okay, but let me just simplify this now. Since that is 0, we already know that so what do we have? Y sub nx is then a sub n of sine of square root of 1/4 minus lambda n x. All right, so x equal to pi. Okay, the solution and the eigenfunction should satisfy the same boundary condition, right? Because y is expanded in terms of yn. So whatever boundary condition is on y, it's the same boundary condition on y. So I think I should emphasize that point also. So, so what does that mean? This is some integer, right? Because sine of this times pi is 0, that means this must be an integer, or we have 1/4 minus lambda n should be n squared. Okay, so we know now the eigenvalue. Okay, so lambda n is nothing but 1/4 minus n squared. Is this clear? This is possible only this quantity is an integer. So sine of n pi is 0, right? Let me know. So that's why, you know, I have written it. This should be integer, or square of that should be n squared. All right. All right. And that's how I've written that. All right. All right. So we have to consider what about the Green's function? We need eigenfunction. So what else? We have to completely write it, including normalization. So I have a y sub n x. The eigenfunction is now a sub n. What is it? Here it is. Yeah. A n times sine of nx. I can write it like this. With n, the n is all given here. All right. Since L is Hermitian operator, I know I can. It should satisfy the orthonormality property. Okay, that we are now using that property too. Otherwise, I cannot do that. So we have. I think I can get rid of all these things now. All right. So we also have what? Between 0 to pi, this is the domain which I'm trying to solve. I should have a square n sine square of nx dx should be 1, should be normalized. Okay, so I can calculate a sub n. What is this? This is 1 minus cosine of 2nx, right? Over 2. Right. So between 0 and pi, what happens to this quantity? The second term, cosine of 2nx between 0 to 2 pi, when you evaluate, it's 0, right? Sine of 2nx or 2n, that will be 0. The only thing that you have is then the first term, which is what, a square n over 2 dx is becoming p. I have this, right? Is equal to 1. Okay. Contribution is coming only from the first term, or I have an this. So this implies x a square n over 2 is equal to 1, or a sub n is nothing but square root of 2 over 5. So I do know the complete eigenfunction including the normalization, which is nothing but square root of 2 over pi times sine of nx. Alright? So we have the eigenvalue here, we have now the eigenvector here. Okay? So we are ready to calculate the Green's function now. So my Green's function is nothing but summation n going from 0 to y n x, y star ns, z lambda n. So it is nothing but summation n going from 0 to infinity of y n x, that is that. So that is equal to 2 over pi sine of nx sine of nz divided by 1/4 minus n squared. It's a function of two variables. That's it. Now that we have this, we can calculate the solution, right? The solution is then the problem. A to B, in this case the domain is 0 to pi, right? G of xz, this is the part that you have to worry about. F of z dz, I mean, this is a common mistake most of us do. So I just want to point out, this is f of x, right? So convert the variable to sine of 2z, because otherwise you will have the integration mixed up, you will get incorrect answer because the integration variable is z. If you had put sine 2x, of course you'll not integrate over that. So in this formula, or this is the inhomogeneous term, right, sine 2x. Immediately write f of z because that's what is the formula. So make that a sine 2z, otherwise your results will be incorrect. Okay, so 0 to pi of all these things. 2 over pi. I can actually 2 over pi, right? Summation n equal to 0 to infinity. Sine nx I can pull out because we are not integrating over that variable. And I have 1/4 minus n squared I pull out of the integration. And here I have this variable, sine of nz, and this one I will put sine of 2z dz. So this is the integral. If you put sine of 2x, it will be pulled out and you will get incorrect answer. So watch out for that. And what is this integral? Sine nz sine 2z. You've come across this before. Again, think of this as 2 sine A sine B, so cosine of A minus B minus cosine of A plus B, and it will contribute only when the arguments are the same. Okay. And so this is really, so if you do, so it's, you do have n minus 2, right? N has to be equal to 2. And it's also, you have a factor of pi also, I think. So half of that integral, because this has to be 2 sine A sine B, right? So you have to multiply and divide by 2. And integration of dz will give you pi. So this is nothing but pi over 2, and n has to be equal to 2. So that is the value. These are orthogonal functions, so you should know this. Okay, we have done this before. So sine A, sine B, cosine, all of them will follow this kind of a property. Okay, whatever is the integral, half of that, and these two arguments have to be the same. Okay, n has to be equal to the same. Okay, so that's the property. If you've forgotten that, you just go back to separate that, 2 sine A sine B, right, plus cosine of A minus B minus cosine of A plus B. And cosine, over 0 to pi, and integrate to 0. The only time cosine of A minus B will also be 0 unless A equal to B. So that's where you get that integration over dz only you get. So that's your solution. So that y of x in this case is again n equal to 2. So it's nothing but 2 over pi. And since n equal to 2, the summation will go away. Only in this infinite range, only one of them will contribute. So it's nothing but sine of 2x over 1 over, it's 2, right? 2 squared is 4. And then I have pi over 2. Okay, so that will also cancel. Okay, so that is the end result in this case. Just simplify that, that's all. This is all gone, so sine over 2x and denominator. Alright, so it's very simple actually. It's a different methodology, but it's very simple. All you have to do is solve the eigenvalue equation basically, and get the eigenvalues and the eigenvectors, construct the Green's function, and then use that, apply that formula. That's your solution is nothing but integral of a to b Green's function times the inhomogeneity term, right? dz. So you can do that, and it's just grounded on this one principle that any solution, any function can be written in terms of an infinite basis set. And that basis set happens to be your eigenfunction of this, Hermite, of this linear Hermitian operator equation. Like an eigenvacuum value equation, Hermitian, matrix you have, it has a forms a complete basis set. That's all. So it starts from that idea of, and then it exploits everything, right? And then it's like, how can I make it, if I differentiate, how can I make it Hermitian, blah, 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 all that stuff, it went on. So there's a lot of other things, but the general principle is fairly, is commonly used, and that's why I gave that example, Homo problem, just to know that any function can, if you have, complete set or basis set, you can expand in terms of later on a vessel or whatever it is, any function, you can expand, because there's our eigenfunctions, right? So that's why I gave that example to appreciate what we are going to be doing today, but that was a very simple thing, those are all used, those principles are used everywhere. All right, I'm going to stop here. Any questions? All right, so maybe next time, I'll see whether to do stem level first, or because that's also a little bit, messy, a little bit messy in terms because you just have to understand a little bit of quantum mechanics. I have to just prove what is Hermitian operator. For matrices, but I have to start from there. and then talk about the other method, which is based on the fact that L operating on G is the Dirac-Delta function, okay? It's almost like solving a homogeneous differential equation, and then from there we'll construct the second solution. I mean, how to write the solution of inhomogeneous differential equation. That's what we are going to be doing. All right. Homework. Have you done? I mean, yeah. Yeah. No problem. Yeah. I'll give you a homework problem. Oh, I know what I want to discuss. Today is what, October 6th, right? We have a second test on October 20th, right? But that's also the day we have the bullet lecture. When is it? I thought, is it, when is test number 2? Is it 20th or 28th?
20th.
I somehow remember 20th, I mean, right? If that's the day, we may want to change the date, that's why we can discuss it next, okay. No, I thought you did, yeah. If it is 20th, we may want to change it.
It's 20th.
Yeah, we need to change that because bullet lecture is 7 o'clock and you may be done, you may not have enough time to finish it up, right? So we can maybe postpone the test to Tuesday, following Tuesday.
Tuesday. 24th.
24th, yeah. Is it fine? Yeah. Because I know some of you will be part of SBS and maybe you have to do certain things for that. And we may not have enough time to, not have somebody.
25th, not 24th. That's the deadline. 25th, not 24th. 24th is the deadline.
Okay, so we'll just, I'll just, remind you again, but I just want to discuss that first. Is it okay to postpone it?
Can we move it to the 27th, or is that too far away?
Too far, because I want, you understand, in terms of materials, I want that to be,
Yeah.
that's what I'm trying, every 1 month I'm trying to do it. Otherwise, the other one is closer, right? I mean, that's what I'm trying to do. Then you'll have to study more things for it. So everything has fixed amount within a month, right? It's already postponing by 4 days, so, yeah.
Thank you.
Okay, welcome.